There is a sound that echoes across time, not through air, not through space, but through something deeper. It's the silent rhythm of the sun, a steady pulse that never stops. You've never heard it, and yet, it has shaped everything you've ever known. Before there were trees, before the oceans moved, before sleep ever touched your eyelids, this rhythm was already playing. The sun, that great fire in the sky, is more than just heat and light. Inside, it breathes. It hums. It pulses with patterns so vast, so ancient, that even time listens. And here, on Earth, we've followed that music since the beginning, not with ears, but with seasons, with tides, with the rise and fall of every living thing. Tonight, in this still moment, you are invited to hear the sun, not through sound, but through story. Not through music, but through memory. This is not a tale of explosions, or chaos, or noise. It is a journey through harmony, through the quiet mechanics of life itself, through the secret symphony that plays in the silence between stars. So close your eyes now. Let your breath match the rhythm of the distant light, and drift gently into the story of a star that never stopped singing, and the world it built with its invisible notes. You are not just hearing this. You've always been a part of it. Welcome to the sun's secret symphony. The sun is not silent. Space itself may be a vacuum, a place where sound cannot travel, but that does not mean nothing moves. Deep inside the sun, a rhythm pulses. A tremor begins in the core, where hydrogen fuses into helium and ripples outward through a boiling sea of plasma. These movements are not random. They follow patterns, pulses, waves. Though we cannot hear them, they are real. Scientists once thought the sun was a constant, unchanging blaze in the sky. But today, we know better. The sun hums. It vibrates. It echoes with a sound too deep for ears. The study of these vibrations is called seismology. It's the science of listening to a star's heartbeat. Just as geologists use earthquakes to map the Earth's interior, astrophysicists use solar sound waves to understand the sun's inner structure. These waves cause the sun's surface to rise and fall ever so slightly, tiny oscillations, thousands of them, rippling across its surface every second. They are not loud. They do not roar. But they are persistent. The sun speaks in a language of motion. Its rhythm has remained unchanged for billions of years. At the heart of the sun lies its engine, the core. Here, temperatures soar above 15 million degrees Celsius. Nuclear fusion converts hydrogen into helium, releasing an incredible amount of energy. This energy pushes outward, balancing the immense gravitational pull trying to collapse the star inward. But with each fusion event, pressure is released unevenly, creating vibrations. These become sound waves, acoustic signatures traveling through the sun's interior. They bounce, they interfere, they resonate. And with the right instruments, we can see them. The rhythms are not chaotic. They are patterned. The sun plays a deep, slow symphony. Some waves last just 5 minutes. Others cycle over days, weeks, even decades. The well-known 11-year solar cycle, the rise and fall of sunspot activity, is just one layer of this complex music. Beneath that lie slower, longer pulses, solar rhythms so vast in scale, we are only beginning to grasp their meaning. Each pulse shapes solar wind, magnetic storms, and radiation flow. The sun doesn't just shine. It breathes. It pulses like a living thing. This rhythm has shaped more than just itself. It has shaped us. The Earth was born within this pattern, emerging in an orbit shaped by the sun's gravitational dance. Its axis, its seasons, its weather, all synchronized to the sun's influence. Over billions of years, life evolved in harmony with solar light and heat. From the smallest microbes in Earth's first oceans to towering forests and mammals, every living thing grew up under the beat of this invisible drum. Even now, our sleep, our heartbeat, our moods are influenced by sunlight. And it's not just light. The solar wind, streams of charged particles, flows outward from the sun in waves, carrying echoes of those same inner vibrations. When they reach Earth, they stir our magnetic field, power auroras, and sometimes disrupt our satellites. These are not random gusts. They follow the rhythms beneath the surface. The sun's pulse is both quiet and immense. It reaches across the void, touching everything. Seismology has revealed more than just internal waves. It's shown us how the sun rotates faster at the equator than at the poles. It's mapped mysterious flows of plasma beneath the surface, giant rivers of motion wrapping around the star. And it's given us a window into the future. By studying shifts in these patterns, Scientists can now predict solar storms, flare cycles, and long-term changes in solar output. The sun is not as stable as it seems. Its pulse evolves, slowly but surely. Imagine standing on a timeless beach, with no wind, no sound, just a faint vibration beneath your feet. That's what the sun's core feels like, an endless pressure, pulsing, guiding, shaping the future. These movements take thousands of years to travel from core to surface. By the time the energy reaches us, it has already lived through ages. What we feel as sunlight is ancient. Every ray is a memory. Every photon was born from a fusion event that happened eons ago. The sun is a time machine, and its pulse is the ticking of cosmic time. Yet for all its power, the sun's heartbeat is fragile. It is steady, but not immortal. As it consumes hydrogen, the balance begins to shift. Its core shrinks. Fusion accelerates. The rhythm changes. Not today, not tomorrow, but one day, the tempo will rise. The music will grow louder. And eventually, the sun will become unstable. Its beat will no longer guide life, but end it. The same pulse that once nurtured Earth will become a signal of its decline. We live in a lucky era, a sweet spot in stellar evolution. The sun is middle-aged, stable, generous. But already, we can detect the subtle signs of aging. Solar cycles are shifting. Fluctuations are growing. The rhythm is beginning to lean forward, just slightly. And though we may not live to see its end, we are part of its arc. Our lives, our history, our future are written into that deep, solar rhythm. And perhaps most haunting of all is this: when the sun's music finally ends, when fusion stops and silence takes hold, there will be no one left to hear it. The sound will fade not with a scream, but with stillness. But until that moment, it plays on. A giant, burning, pulsing star, silently singing the universe's oldest song. So tonight, as you lie still, know this: you are not drifting alone. The rhythm you cannot hear still guides you. The warmth you feel on your skin began as a tremor in a star. The light outside your window carries a pulse older than Earth itself. You are living inside a story of resonance, of balance, of breath. This is the pulse of a giant. Space is known for its silence. Without air or water to carry sound, there's nothing to hear in the traditional sense. But inside the sun, a different kind of motion is always happening, not sound as we know it, but pressure waves moving through hot plasma. These vibrations ripple through the star's interior in complex, rhythmic patterns. Even though space outside is silent, inside the sun there is a constant physical movement, a resonance that scientists have learned to study. In this way, the sun carries sound within it, though no one can actually hear it. This internal activity begins in the sun's core, where nuclear fusion creates intense energy. That energy pushes outward, creating waves that travel through the different layers of the star. These waves are known as pressure waves, or P waves. They aren't sound waves in the conventional sense, but they behave similarly, compressing and expanding the material as they pass through. The difference is that in the sun, these waves move through superheated gas and plasma, not through air. As these waves rise from the core and pass through the convective zone, they leave behind measurable effects. The sun's surface lifts and dips ever so slightly in response to them, creating visible oscillations. Although these movements are incredibly small, scientists can detect them with special instruments. Over time, a picture begins to emerge, a map of the sun's internal behavior, drawn from waves we cannot hear. The field that studies these waves is called aleoseismology. Much like geologists study how seismic waves travel through Earth to learn what lies beneath the surface, astrophysicists analyze solar vibrations to understand the structure of the sun. They use sensitive telescopes and detectors to measure surface motion, and from that, they reconstruct what's happening deep inside. It's like listening without ears, turning motion into information. Aleoseismology has revealed much about the sun's internal layers. For instance, we now know that the sun doesn't rotate at the same speed everywhere. The equator spins faster than the poles, a detail uncovered by examining the timing of wave motion. These insights help us understand the life cycle of stars, not just ours but others across the galaxy. The sun is a reference point. Its rhythms help define the nature of stars in general. One of the surprising things about the sun's internal waves is how orderly they are. Despite the sun's intense energy and chaotic appearance, the waves form consistent, repeatable patterns. These patterns change slightly over time, but many of them are remarkably stable. This tells us that the sun, even in its complexity, is governed by deep laws of physics. Its core pulses with energy, and those pulses travel outward like signals in a quiet, invisible drum. Over years of observation, scientists have detected thousands of these wave patterns. Some occur in cycles of minutes, others stretch over days. When viewed as a whole, these rhythms begin to look like a natural clock, a series of repeating signals that reflect the heartbeat of a star. These patterns allow scientists to monitor solar changes, predict solar activity, and refine models of stellar behavior. The Sun, in a way, becomes readable. To study these waves, scientists often use space-based observatories such as the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO. These instruments measure tiny Doppler shifts on the Sun's surface, changes in motion that suggest rising or falling material. By collecting this data over months and years, researchers can build models of how the waves move through the Sun's interior. These discoveries don't just help us understand the Sun itself. They also help explain how the Sun influences Earth. Solar waves are connected to magnetic activity, which in turn affects solar storms. These storms can disrupt satellites, damage power grids, and influence Earth's climate in subtle ways. By understanding solar rhythms, we can prepare for these effects, even years in advance. Even more fascinating is how this approach, studying something we cannot hear, has changed our view of stars in general. Scientists now use a similar method, called astroseismology, to study distant stars. By detecting tiny changes in their brightness caused by internal waves, we can learn about their size, age, and internal structure. All of this comes from understanding the Sun first. Helioseismology is not just a scientific method, it's a way of revealing the hidden life of a star. The Sun's vibrations tell us what's happening where no probe can go. We cannot visit the solar core, but we can read its messages. We cannot touch the fusion processes at the center, but we can see how they ripple outward. In this way, sound, or the movement of pressure, becomes a language, one we've learned to decode. There is no need for dramatic visuals or booming audio. The quiet pulse of a star is powerful enough. It shapes the environment of planets, it influences space weather, and it tells the story of energy transfer at the most fundamental level. The Sun is not just a ball of fire in the sky. It is a carefully layered, constantly moving engine of light, whose internal structure hums with quiet patterns. These patterns guide solar evolution, and they provide one of the few windows we have into stellar interiors. As we listen more closely, we find more questions. How will the Sun's vibrations change as it ages? When it expands into a red giant, will these rhythms disappear, or will they transform into something more chaotic, more intense? What can we learn by studying the differences between our Sun and other stars of different sizes and stages? These questions now guide research missions around the world. Ultimately, the ability to hear the Sun, without sound, is one of the great scientific achievements of the modern era. It demonstrates how observation, mathematics, and imagination can work together to explore something unreachable. We may not experience these waves the way we hear music, but through our tools and our minds, we interpret their rhythm. The Sun may never speak, but it always resonates. And in that resonance, there is meaning. A slow, deep signature that says, I am alive. I am burning. I am changing. Listen close enough, and you'll find that even in the silence of space, there is something waiting to be understood. The Sun is not only a source of light and heat, it is also a restless engine, constantly pushing energy outward in all directions. These outflows, made up of particles and waves, stretch across the solar system and shape the environments of the planets caught in their path. Among them, Earth stands uniquely shielded. What protects our planet isn't just its distance from the Sun, but an invisible shield sculpted by the interaction of the Sun's waves and Earth's own magnetic field. This shield is what keeps us safe, and without it, life as we know it would not exist. At the center of this relationship is the solar wind, streams of charged particles constantly flowing from the Sun. This wind isn't random. It follows patterns and pulses, many of them linked to deeper movements within the star itself. Pressure waves inside the Sun help push these particles outward, and the way the Sun rotates and shifts over time changes the speed and intensity of these flows. While invisible to the naked eye, solar wind carries the fingerprint of the Sun's internal rhythms. As this solar wind reaches Earth, it encounters the magnetosphere, an invisible bubble created by Earth's rotating, iron-rich core. This magnetic field stretches into space, forming a protective layer that bends the charged particles away from the surface. Without this magnetic field, solar wind would strip away our atmosphere over time, just as it did to Mars. But Earth's shield holds strong, and the interaction between these forces becomes one of the most beautiful and vital dances in the solar system. When the sun's waves grow stronger, so does the solar wind. This often happens during solar storms or periods of heightened magnetic activity. These intensified waves crash into Earth's magnetosphere with greater force, compressing its shape and sending energy deep into its structure. The result is not just a shift in the planet's outer defenses, but also a display of light in the sky, auroras. These glowing patterns near the poles are the visible outcome of invisible rhythms. Auroras occur when charged particles from the solar wind spiral along magnetic field lines and enter Earth's upper atmosphere. As they collide with gas molecules, mostly oxygen and nitrogen, they excite those atoms, causing them to emit light. The colors of the auroras vary depending on the type of gas and the altitude of the collision. Green is most common, but red, blue, and violet can also appear. These lights flicker and dance, echoing the pulse of solar rhythms. But auroras are only the visible sign. Beneath the light show, Earth's systems are constantly adjusting to the energy coming from the sun power grids can feel the strain. Satellites may become unstable. Communication systems might falter. All of this traces back to how the sun's energy waves interact with our planet's shield. And behind it all is a kind of pulse, a reminder that even in stillness, the sun is never quiet. The rhythm of the sun can be subtle. During quiet solar periods, the wind is gentle, and the magnetosphere stretches wide and undisturbed. But even then, small pulses still arrive. The sun breathes energy outward constantly, and Earth responds. There's a balance here, delicate and ongoing. Over long timescales, scientists have observed patterns in how the magnetosphere behaves, closely tied to solar cycles. These cycles, lasting about 11 years, reflect the rise and fall of solar magnetic activity. When solar activity peaks, sunspots increase, and solar flares become more frequent. These flares release bursts of energy that intensify the solar wind. Coronal mass ejections, huge releases of plasma from the sun's outer atmosphere, can follow, pushing massive waves of particles through space. If one of these reaches Earth, it can dramatically reshape the magnetosphere, even briefly reversing magnetic polarity in localized regions. These events are rare but significant. What makes these solar events important isn't just their intensity, it's their predictability. Because the sun's waves follow certain patterns, scientists can forecast changes in the solar wind and prepare for their impact. Helioseismology, satellite data, and magnetic readings from Earth all contribute to these models. By reading the sun's rhythms, we can anticipate when the sky might shift. It's a kind of space weather forecast, rooted in the hidden waves of a star. Over time, this relationship between the sun and Earth has become more than scientific. It's poetic in its structure, one giant body sending energy across a gulf of space, and a smaller world quietly responding. Earth doesn't fight the sun's wind. It bends, absorbs, and redirects. In doing so, it protects everything on its surface. This balance has lasted billions of years. It is not static, but it is resilient. The strength of Earth's magnetosphere is not infinite. It weakens and strengthens over time. Magnetic poles wander. Reversals occur, events where the north and south magnetic poles switch places. These changes happen slowly, over thousands of years, and during such periods, the shield may become patchy or unstable. Still, Earth has endured multiple reversals without catastrophic damage. The sun's waves keep coming, and the magnetosphere keeps adapting. Beyond Earth, other planets experience the solar wind in different ways. Mars, once more Earth-like, lost its magnetic shield long ago. Now, exposed to constant solar wind, its atmosphere is thin, and its surface dry and cold. Jupiter, with its massive magnetic field, creates immense auroras more powerful than anything on Earth. These examples show how vital the magnetic shield is, and how the sun's energy shapes more than just our own skies. For Earth, the rhythm of the sun is more than a distant force. It is a partner in a silent exchange. The sun pulses with energy, and Earth answers with its shield, its sky, and its light. In this way, Earth's sky is shaped not only by weather or clouds, but by invisible waves that began millions of kilometers away. The auroras are reminders, colorful signals that we are part of something larger. From space, the auroras look like halos of green and red wrapped around the poles. They shimmer and shift in sync with solar wind variations. These lights are not constant. They follow the rhythm of the sun. Astronauts aboard the International Space Station often watch them in awe. Some have described them as Earth's breathing, slow, glowing, and alive. It is not a poetic exaggeration. It is a visual truth rooted in physics. The more we study these interactions, the more we understand how life is protected not just by distance or temperature, but by motion. The motion of the Earth's core, the movement of magnetic fields, the pressure waves of the sun, all play a role in maintaining the delicate conditions that allow life to exist. Without these invisible shields, Earth would be vulnerable to radiation, particle storms, and atmospheric decay. And still, the sun continues its rhythm. Even now, it sends out pulses, not to destroy, but as part of its nature. Earth does not resist them, it has learned to live within them. Our magnetic field, born from deep within, responds in kind. Together, the two systems form a dynamic balance. Each wave from the sun is absorbed, deflected, or redirected. And each moment of pressure from outside reminds Earth to stay in motion within. This balance is not forever. In future chapters, the rhythm will grow louder, the solar wind stronger, and the magnetosphere weaker. But for now, in this time, Earth and sun remain locked in harmony. The sky glows not from sound, but from energy, and the story it tells is one of connection. Invisible, powerful, and enduring. Long before thermometers, satellites, or climate models, the sun was already shaping Earth's weather. Its brightness, its moods, and its rhythm set the pattern for temperature, seasons, and long-term climate shifts. We often think of the sun as constant, but its light is not perfectly steady. Across years and centuries, its energy output rises and falls in cycles. Cycles that leave fingerprints in the ice, in tree rings, and in the stories of civilizations. Solar cycles are measured in roughly 11-year intervals. During a solar maximum, the sun becomes more active. Dark sunspots appear on its surface, along with bursts of energy called solar flares. These changes increase the total energy Earth receives. At solar minimum, the sun is quieter, with fewer sunspots and less energy reaching the planet. These cycles may seem small in magnitude, but over time, they shape how much warmth our atmosphere holds and how stable our climate remains. One of the clearest historical signs of this connection came during the Little Ice Age. From the early 1300s to the mid-1800s, Europe and parts of the Northern Hemisphere experienced cooler temperatures, harsh winters, and shorter growing seasons. Glacier expanded. Rivers like the Thames in London froze over. While volcanic activity and ocean circulation played roles, a significant factor was reduced solar activity, particularly a period known as the Maunder Minimum, when sunspots nearly vanished for decades. The drop in solar energy helped tip Earth's climate toward cold. Even further back, the link between the sun and weather was noted, though not understood. Ancient civilizations carefully tracked solar patterns. The Mayans, Chinese, Greeks, and Egyptians observed solar alignments, eclipses, and the changing height of the sun in the sky. They built monuments aligned to solstices and equinoxes. They recorded strange occurrences, failed crops, long winters, or dry years, all tied to shifts in sunlight. Without modern science, they still knew the sun set the rhythm of the Earth. This rhythm extended to seasons. As Earth orbits the sun, its tilted axis causes changes in the angle and intensity of sunlight, creating winter and summer. But subtle changes in solar output amplify or reduce those effects. A slightly stronger sun during summer can trigger heat waves. A quieter sun can soften winters or deepen cold snaps. Over centuries, these slight changes accumulate, shifting climate zones and water patterns. Ice ages themselves are partially linked to long-term solar changes combined with Earth's orbital variations. The sun also affects rainfall. Studies of monsoon patterns in Asia and Africa reveal links to solar cycles. Stronger solar activity tends to intensify monsoon seasons, increasing rain and river flow. Weaker activity can lead to droughts. In regions dependent on agriculture, this solar influence is critical. Famines, migrations, and societal collapse have all followed prolonged climate changes driven in part by variations in sunlight. Today, modern instruments track solar energy with precision. Satellites measure the total solar irradiance, the amount of energy the sun delivers to Earth. These observations help scientists monitor trends, understand natural climate variation, and separate solar influence from human-caused climate change. While greenhouse gases now dominate modern warming trends, the sun's role remains part of the bigger picture, especially for long-term cycles. Sunspots themselves are not simply blemishes. They are cooler regions of intense magnetic activity. When their number rises, it signals a more active Sunday. But paradoxically, even though sunspots are darker, increased solar activity overall means more light and energy emitted. So, a higher number of sunspots generally leads to warmer global conditions. These surface patterns are the visible signs of deeper processes within the sun: pulsations, flows, and magnetic twists. Solar flares and coronal mass ejections also have short-term effects. These bursts of charged particles can heat Earth's upper atmosphere, expanding it and affecting satellite orbits. They can disrupt communication systems and create temporary warming effects. While these events are brief, they demonstrate how rapidly solar weather can influence Earth's environment, beyond the slow rhythm of cycles. The impact of the sun extends into the oceans. Solar cycles influence sea surface temperatures and currents like El Niño and La Niña. These ocean patterns affect weather worldwide, from hurricanes in the Atlantic to droughts in South America. Though not the sole cause, solar variation nudges these systems, shaping the timing and strength of events that affect millions. In polar regions, ice cores provide a timeline of climate and solar behavior. Tiny air bubbles trapped in ancient ice contain clues about past solar activity. When cosmic rays from deep space reach Earth, they interact with the atmosphere to create isotopes like carbon-14 and beryllium-10. During times of low solar activity, more cosmic rays enter, leaving more isotopes. When the sun is active, its magnetic field deflects cosmic rays, and fewer isotopes appear. These records match periods of warming and cooling on Earth, linking solar rhythm with environmental change. Despite its immense influence, the sun is not a wild force. Its changes are subtle, often slow, and usually balanced. It is not the cause of every storm or drought, but it sets the boundary conditions within which Earth's climate unfolds. It is the silent conductor of a vast, interconnected system, where light becomes warmth, and warmth becomes wind, rain, and snow. The sun's rhythm is more than just energy. It is timing. Crops grow under patterns of light. Animal migrations follow solar clocks. Trees form rings based on seasonal cycles set by sunlight. Humans, too, feel the influence, from mood changes in winter to productivity patterns linked to daylight. Even without understanding the mechanics, life on Earth has always responded to the sun's timing. It is built into biology. With every solar cycle, Earth receives a slightly different version of its usual energy. These changes are natural, recurring, and ancient. But in recent centuries, human activity has added another layer. Greenhouse gas emissions now amplify warming, sometimes masking or intensifying natural cycles. Still, solar influence continues to play a role. Understanding that role helps scientists refine climate models and distinguish natural variation from human impact. Looking forward, the sun will continue its cycles, some stronger, some weaker. New data suggest we may be entering a period of slightly reduced solar activity. What that means for climate remains uncertain. It may provide a small cooling influence, but not enough to offset the rapid pace of human-driven warming. Still, it reminds us that the sun's rhythm hasn't stopped. It is always there, setting the baseline from which all weather unfolds. Understanding the sun's influence is not just about science. It is about memory. Ancient people watched the skies and responded with reverence. They marked the solstices, celebrated harvests, and feared eclipses. They understood the sun not as a god, but as a giver of life and a changer of fate. Their stories, carved in stone and told across generations, reflect the same truth we now verify with satellites and data. The sun drives the weather, not just in the sky, but in human history. The next time a warm wind rises or a cold front moves through, remember, it is part of a larger rhythm, one that begins millions of kilometers away. The clouds, the rain, the storms, they are shaped, in part, by the beat of a star. And though that beat is slow, it never stops. Long before life learned to walk, speak, or even think, it learned to follow the sunlight wasn't just warmth or energy. It was a signal. A daily message. It told life when to wake, when to grow, when to rest. Over time, light became the earliest form of timekeeping, and from it, nature began to build its first clocks. At the center of this system was something called the circadian rhythm, a built-in, 24-hour cycle that allows living organisms to align their behavior with the day-night rhythm of the planet. Plants were among the first to evolve this timing system. As they turned their leaves toward the dawn, they weren't just soaking in energy. They were obeying an internal signal wired directly to light. This biological timing didn't come from clocks or calendars. It came from the consistent rhythm of sunrise and sunset. Photosynthesis, The process that allows plants to turn sunlight into energy depends entirely on this connection. It is not just a reaction to light, it's a dialogue. When light appears, special proteins within plant cells activate, triggering a chain reaction that converts carbon dioxide and water into sugars. Oxygen is released as a byproduct, but the speed, intensity, and pattern of this reaction depend on the time of day. Plants are most efficient in the morning. By afternoon, their systems begin to shut down. This rhythm is so precise that plants in complete darkness will still try to follow it for several days. This internal clock is not limited to plants. Animals, too, develop their own biological rhythms based on light. Birds know when to migrate. Nocturnal creatures know when to emerge. Humans, as well, have internal systems tied to sunlight. The rise and fall of melatonin, the hormone that regulates sleep, is triggered by the presence or absence of light. Our energy levels, hunger patterns, and even mood are shaped by sunlight. In essence, the sun became a timekeeper not just for Earth's orbit, but for the lives unfolding on its surface. The development of circadian rhythms helped life organize itself. With time structured into day and night, species could specialize. Some thrived in daylight, others in darkness. This separation reduced competition and increased survival. It also allowed ecosystems to stabilize. Predators and prey, pollinators and plants, each found their window within the larger rhythm set by the sun. Over millions of years, evolution fine-tuned this relationship. Organisms developed light-sensitive proteins called cryptochromes and photoreceptors, allowing them to sense changes in sunlight with great accuracy. These molecular tools acted like internal sensors, turning solar rhythms into biochemical instructions. Light didn't just guide behavior, it shaped development, growth, and reproduction. Even the simplest organisms, like bacteria and single-celled algae, show light-responsive behavior. Cyanobacteria, among the earliest life forms to perform photosynthesis, began structuring their processes around daylight. Their survival depended on it. For them, sunlight wasn't just food, it was a countdown, a start and stop signal for daily function. As life moved from water to land, the need to track sunlight became even more important. On land, temperature changes were more extreme. Days were brighter, nights darker. Organisms that could anticipate sunrise or sunset had an advantage. They could prepare, conserve energy, or seize resources before others. Those that followed the sun's timing closely tended to survive, reproduce, and pass on their light-sensitive traits. In forests, plants began to compete for sunlight. Tall trees blocked light from reaching the ground. In response, some plants evolved to track the sun's movement across the sky, a process called heliotropism. Others developed large, flat leaves to capture every bit of scattered light. Still others bloomed only at certain times of day, when light conditions were optimal. In every case, the sun's rhythm was the guiding principle. Flowers, for instance, often open and close based on the time of day. Some bloom at dawn, others at dusk. Pollinators respond accordingly. Bees arrive in the morning, moths at night. This synchronized behavior is an example of coevolution, where two species evolve together, bound by the same light-based schedule. The sun doesn't just fuel life, it organizes the interactions between living things. Long before life learned to walk, speak, or even think, it learned to follow the sunlight wasn't just warmth or energy, it was a signal, a daily message. It told life when to wake, when to grow, when to rest. Over time, light became the earliest form of timekeeping, and from it, nature began to build its first clocks. At the center of this system was something called the circadian rhythm, a built-in, 24-hour cycle that allows living organisms to align their behavior with the day-night rhythm of the planet. Plants were among the first to evolve this timing system. As they turned their leaves toward the dawn, they weren't just soaking in energy. They were obeying an internal signal wired directly to light. This biological timing didn't come from clocks or calendars. It came from the consistent rhythm of sunrise and sunset. Photosynthesis, the process that allows plants to turn sunlight into energy, depends entirely on this connection. It is not just a reaction to light, it's a dialogue. When light appears, special proteins within plant cells activate, triggering a chain reaction that converts carbon dioxide and water into sugars. Oxygen is released as a byproduct, but the speed, intensity, and pattern of this reaction depend on the time of day. Plants are most efficient in the morning. By afternoon, their systems begin to shut down. This rhythm is so precise that plants in complete darkness will still try to follow it for several days. This internal clock is not limited to plants. Animals, too, develop their own biological rhythms based on light. Birds know when to migrate. Nocturnal creatures know when to emerge. Humans, as well, have internal systems tied to sunlight. The rise and fall of melatonin, the hormone that regulates sleep, is triggered by the presence or absence of light. Our energy levels, hunger patterns, and even mood are shaped by sunlight. In essence, the sun became a timekeeper not just for Earth's orbit, but for the lives unfolding on its surface. The development of circadian rhythms helped life organize itself. With time structured into day and night, species could specialize. Some thrived in daylight, others in darkness. This separation reduced competition and increased survival. It also allowed ecosystems to stabilize. Predators and prey, pollinators and plants, each found their window within the larger rhythm set by the sun. Over millions of years, evolution fine-tuned this relationship. Organisms developed light-sensitive proteins called cryptochromes and photoreceptors, allowing them to sense changes in sunlight with great accuracy. These molecular tools acted like internal sensors, turning solar rhythms into biochemical instructions. Light didn't just guide behavior, it shaped development, growth, and reproduction. Even the simplest organisms, like bacteria and single-celled algae, show light-responsive behavior. Cyanobacteria, among the earliest life forms to perform photosynthesis, began structuring their processes around daylight. Their survival depended on it. For them, sunlight wasn't just food, it was a countdown, a start and stop signal for daily function. As life moved from water to land, the need to track sunlight became even more important. On land, temperature changes were more extreme. Days were brighter, nights darker. Organisms that could anticipate sunrise or sunset had an advantage. They could prepare, conserve energy, or seize resources before others. Those that followed the sun's timing closely tended to survive, reproduce, and pass on their light-sensitive traits. In forests, plants began to compete for sunlight. Tall trees blocked light from reaching the ground. In response, some plants evolved to track the sun's movement across the sky, a process called heliotropism. Others developed large, flat leaves to capture every bit of scattered light. Still others bloomed only at certain times of day, when light conditions were optimal. In every case, the sun's rhythm was the guiding principle. Flowers, for instance, often open and close based on the time of day. Some bloom at dawn, others at dusk. Pollinators respond accordingly. Bees arrive in the morning, moths at night. This synchronized behavior is an example of coevolution, where two species evolve together, bound by the same light-based schedule. The sun doesn't just fuel life, it organizes the interactions between living things. The oceans, vast and seemingly endless, do not move on their own. They breathe with the sun, pulse with the moon, and sway to invisible patterns that stretch across time. While we often think of the sea as unpredictable or chaotic, its movements follow rhythms, set in motion by the energy of the sun and the subtle gravitational touch of the moon. Together, these celestial forces guide waves, tides, and currents, making the oceans not just bodies of water, but instruments of planetary balance. Solar energy is the primary engine that drives wind on Earth. When the sun's rays warm the surface unevenly, more at the equator than at the poles, it causes air to rise and fall in patterns. This differential heating produces large-scale wind systems, like the trade winds, which push ocean water across the globe in regular, sweeping currents. These winds guide the movement of entire seas. The Pacific, Atlantic, and Indian Oceans all circulate in giant loops, or gyres, because of this solar-powered wind. As warm water is moved from one region to another, it alters air temperature and humidity above it, directly shaping climate. Coastal areas become wetter or drier, warmer or cooler, depending on these flows. In this way, the sun does not just heat the surface, it orchestrates the movement of the entire climate system through the oceans. One of the most striking examples of this relationship is the El Niño a Southern Oscillation, ENSO. This cycle, driven by changes in ocean temperatures in the central and eastern Pacific, can affect weather patterns across the entire planet. During an El Niño event, trade winds weaken, allowing warm water to accumulate along the South American coast. This extra heat in the ocean changes atmospheric pressure, leading to increased rainfall in some areas and drought in others. It can disrupt fishing industries, alter monsoon patterns, and even shift hurricane tracks. The opposite of El Niño is La Niña, when trade winds strengthen, pushing warm water back toward Asia and cooling the eastern Pacific. This too has global consequences. Both phases are natural parts of Earth's rhythm, one that depends on the sun's influence on oceanic wind systems. These events are not random. They are tied to solar-driven patterns that echo across years, decades, and even centuries. The sun's role in shaping these events is not always direct. It sends energy to Earth, but how that energy is absorbed, stored, and released by the ocean adds a layer of complexity. Water has a high heat capacity. It warms slowly and cools slowly. This means oceans act like a massive memory bank for solar energy, absorbing heat during sunny periods and releasing it during cooler ones. This delayed effect stabilizes global temperatures but also allows for oscillations like ENSO to occur. Beyond temperature and wind, tides are another form of ocean rhythm, though they are more closely tied to the moon. Still, the sun plays a role here too. Tides occur because of gravitational forces. The moon pulls at Earth's oceans, causing them to bulge. But when the sun and moon align during full or new moons, their gravitational forces combine, leading to higher spring tides. When they are at right angles, we see lower neap tides. This solar-lunar interaction ensures that even the rise and fall of coastal waters are touched by starlight. Tides regulate more than just water levels. They shape the behavior of marine life. Many ocean organisms, like crabs, oysters, and even certain fish, have evolved to move, feed, and reproduce in sync with tidal rhythms. Coral spawning, for example, is often tied to lunar and solar cycles. These events happen simultaneously across massive reef systems, timed with precision that suggests an ancient, shared biological clock connected to celestial movement. Ocean currents, meanwhile, act as conveyor belts of climate. The Gulf Stream, for example, carries warm water from the Gulf of Mexico across the Atlantic toward Europe. This current helps keep parts of northern Europe much warmer than other regions at the same latitude. It is sustained by the combination of solar heating, wind, salinity, and Earth's rotation, a process known as thermohaline circulation. If disrupted, this system could lead to drastic shifts in global climate, demonstrating again how deeply climate is tied to ocean rhythm, and, at the base of it, the sun's influence. As Earth's climate continues to change, scientists pay close attention to how oceans respond. A warming sun or changing solar cycle might seem small, but over long periods, these changes can alter current strength, sea level, and rainfall distribution. Already, satellite data and ocean buoys are tracking minute variations in sea surface temperature, wind speed, and current velocity, all to better understand how the ocean's rhythm adjusts to the beat of solar energy. Marine weather patterns are especially sensitive to these rhythms. The formation of tropical storms and cyclones depends on sea surface temperature, which, in turn, depends on solar heating. A warmer ocean leads to more powerful storms, with higher rainfall and stronger winds. A cooler surface reduces that risk. In this way, even natural disasters trace their roots back to patterns in solar input, modulated through the sea. The oceans also affect the carbon cycle. Phytoplankton, microscopic plants floating near the surface, perform photosynthesis, absorbing carbon dioxide and releasing oxygen. Their growth depends on sunlight and nutrients, both of which fluctuate with ocean currents. When upwelling brings cold, nutrient-rich water to the surface, phytoplankton blooms increase. These blooms support entire food webs and also draw carbon from the atmosphere, helping regulate Earth's temperature. Thus, even the ability of Earth to breathe in and out carbon is linked to the way the ocean moves, and how the sun guides that movement. Many cultures throughout history noticed the ocean's rhythm, even without understanding its mechanisms. Ancient Polynesians navigated thousands of miles across the Pacific using wave patterns and star positions. They knew when to fish and when to stay ashore based on the sea's behavior. Coastal tribes in Africa and South America developed rituals and calendars based on tidal flow and seasonal ocean winds. In each case, the ocean was not just water, it was a guide, a living calendar. Modern scientists use computer models to simulate how solar variability impacts ocean systems. They compare historical data with present trends, trying to forecast future changes. While short-term weather remains hard to predict, long-term patterns, driven by ocean cycles, follow more predictable rules. These forecasts help prepare for droughts, manage fisheries, and anticipate extreme weather years in advance. The rhythm of the ocean is slow. It operates on scales much longer than human lifespans. Some patterns take decades to complete. Others, like deep ocean circulation, may take centuries. But this slowness is not weakness, it is stability. It is the reason Earth's climate has remained relatively stable for so long. As long as the sun shines and the moon pulls, the sea will continue its ancient dance, swaying to rhythms older than time itself. Even in silence, the ocean speaks. Its waves whisper the story of solar heat. Its currents tell tales of invisible winds. Its tides rise and fall like breath. To understand the ocean is to listen not just to water, but to the sun, to the moon, and to the deep harmony that links them all. Before alarms, schedules, or electricity, human life moved with the sun. When light rose over the horizon, the day began. When darkness fell, rest followed. This ancient cycle wasn't just a cultural habit, it was rooted deep in biology. Our bodies, like those of all living organisms, evolved to follow the Earth's light-dark rhythm. That connection, forged over millions of years, still controls how we sleep, feel, and function, even today. At the heart of this internal timing system is a biological process known as the circadian rhythm. From Latin, circa diem means about a day. And that's exactly what it is, a natural, 24-hour cycle that influences nearly every system in the body. It governs when we feel alert or tired, when we get hungry, how our body temperature fluctuates, and even how our brain processes emotions. But the master key that controls this rhythm is light. Sunlight, especially the blue spectrum of morning light, acts as a trigger. When our eyes first detect natural light, they send signals to a small region in the brain called the suprachiasmatic nucleus, SCN, located in the hypothalamus. The SCN serves as the body's master clock. It synchronizes all the other internal clocks spread across different organs, tissues, and cells. This synchronization keeps our body working as a coordinated whole. One of the most important hormones tied to this system is melatonin. Often called the sleep hormone, melatonin is produced by the pineal gland in response to darkness. As daylight fades, the SCN tells the pineal gland to begin releasing melatonin, signaling to the body that it's time to wind down. Body temperature lowers. Heart rate slows. Brain activity begins to shift into a quieter, more restful state. When sunlight returns the next morning, melatonin production is suppressed and wakefulness returns. This cycle of melatonin rise and fall creates the foundation of the human sleep-wake cycle. It's why people generally feel alert during the day and sleepy at night. It's also why disrupting light exposure, by staying up late with screens or traveling across time zones, can lead to poor sleep and health issues. Jet lag, for example, occurs when the body's internal clock is out of sync with the external light-dark cycle. Modern life has introduced many challenges to this natural rhythm. Artificial lighting, shift work, and excessive screen use have all made it harder for the body to maintain a healthy circadian pattern. Bright indoor lighting at night confuses the brain, tricking it into thinking it's still daytime. This delays melatonin release, pushes back sleep onset, and can lead to chronic sleep problems. Even the quality of sleep suffers, becoming shallower and less restorative. Despite these disruptions, the body still tries to follow the sun. Research has shown that spending even a few days in natural light, such as camping without electronics, can reset the body's internal clock. People fall asleep earlier, wake up more refreshed, and report better mood and mental clarity. This shows that our connection to the sun's rhythm is not easily erased. It waits, quietly, beneath the noise of modern life. The rhythm of light also affects our emotional state. Melatonin isn't the only hormone linked to sunlight. Serotonin, a neurotransmitter tied to mood and well-being, is also influenced by light exposure. Higher light levels during the day increase serotonin production, which can lead to better mood, higher energy, and improved focus. This is why lack of sunlight during winter months can cause seasonal affective disorder, SAD, a form of depression that lifts when natural light returns. Our immune system also dances to the sun's rhythm. White blood cell counts, inflammatory markers, and even responses to vaccines fluctuate depending on the time of day. These cycles help the body anticipate threats and prepare defense mechanisms more efficiently. Hormones like cortisol, which help regulate metabolism and stress, also follow a strict daily rhythm tied to sunrise. Cortisol levels rise sharply in the early morning to help us wake up and become alert. They fall gradually throughout the day, allowing the body to relax in the evening. Interestingly, the timing of medication and treatment can be optimized by understanding the body's rhythms. A growing field called chronomedicine studies how drug effectiveness and side effects vary with the time of day. Some medications work better when taken in the morning, others are more effective at night. Even chemotherapy has been shown to produce better outcomes when administered in sync with a patient's circadian cycle. In children, the sun's rhythm plays an even more critical role. As their bodies and brains develop, a consistent light-dark schedule helps support proper growth, learning, and behavior. Exposure to morning light improves attention and memory, while regular sleep supported by nighttime darkness promotes physical and emotional development. Sleep disruptions in childhood can affect everything from academic performance to immune function. The elderly also experience changes in their circadian rhythm. As people age, melatonin production decreases, leading to more fragmented sleep and earlier waking times. Understanding how to support older adults with appropriate light exposure, especially in care settings, can improve mood, sleep, and cognitive health. Throughout life, our internal systems continue to respond to the sun's cues. Even in environments where the sun is absent or controlled, like in space or in underground facilities, people require artificial light-dark cycles to stay healthy. NASA carefully designs lighting systems for astronauts on the International Space Station to mimic Earth's day-night rhythm. Without it, sleep quality deteriorates, and mental focus suffers. Light is not a luxury, it is a biological necessity. Our bodies aren't just influenced by the sun, they are shaped by it. The very evolution of the human sleep-wake cycle was driven by environmental light patterns. Our ancestors who stayed active during the day and rested at night had better survival odds. They could see better in daylight, avoid predators at night, and conserve energy more effectively. Over generations, this behavior became biology. It shaped our eyes, brains, and even our DNA. This deep connection to solar rhythm is why modern disruptions feel so unnatural. Staying up late under bright lights, staring at phones, or living without windows creates a kind of biological confusion. The body doesn't know when to rest or activate. This leads to chronic fatigue, mood disorders, and reduced immune function. Yet the solution remains simple: return to the light. Sunlight, especially in the morning, is the most powerful natural signal for resetting our internal clocks. A short walk outdoors within the first hour of waking can anchor the day's rhythm. Dimming lights in the evening and reducing screen time helps melatonin flow naturally. These small changes realign us with the ancient cycle that our bodies still recognize. The human body is not a machine running on schedules. It is a living instrument, tuned to a pattern older than civilization. The sun's rise and fall are still its metronome. Light tells our cells when to divide. It tells our brains when to release hormones. It tells our hearts when to slow down and rest. Every breath, blink, and heartbeat responds, in some way, to light. Even in sleep, the sun's influence continues. Our dreams, brain waves, and memory processes all unfold according to circadian timing. Deep sleep peaks early in the night. REM sleep, associated with vivid dreaming, peaks closer to dawn. These patterns allow the body and mind to heal, reset, and prepare for another day. And when morning light returns, the process begins again. In an age of constant stimulation, it's easy to forget that we were designed to live by light. Our systems aren't broken, they are just waiting for realignment. And the path back is not complicated. It begins with recognizing that every cell, every tissue, every organ still listens for the same signal, the rising sun. When we speak of rhythm, we often think of music or movement. But the truest rhythm we know, the one that governs life itself, is the rhythm of light. It flows from the sun to the earth, and from there, into the deepest corners of our biology. It is the original conductor. And as long as it shines, our bodies will continue to move to its silent, ancient beat. The sun, though vast and ancient, is not always calm. Its rhythm, usually steady and predictable, can suddenly stutter. For all its consistency, there are moments when the sun pulses too hard, too fast, and sends ripples of chaos through space. These are the solar flares and coronal mass ejections, the sun's equivalent of a skipped heartbeat. When they occur, Earth feels the tremor, not with sound or pressure, but with electromagnetic fury. A solar flare is an abrupt, intense burst of radiation emanating from the sun's surface. It happens when magnetic energy builds up and suddenly releases, often near sunspots, dark regions on the sun where magnetic fields twist and snap. These flares can last minutes or hours, sending powerful X-rays and ultraviolet radiation into space. Though they don't travel fast enough to strike Earth directly like a solid object, their energy moves at the speed of light, reaching Earth's upper atmosphere in just over 8 minutes. Coronal mass ejections, or CMEs, are even more dramatic. These are enormous expulsions of plasma and magnetic field from the sun's corona, its outermost atmosphere. While flares are like sudden flashes, CMEs are explosions that hurl billions of tons of charged particles through space. They move slower than flares, taking 1 to 3 days to reach Earth, but their impact can be far more disruptive. Under normal conditions, Earth's magnetosphere, the magnetic bubble surrounding our planet, shields us from the solar wind, the continuous stream of particles flowing from the sun. But when a CME hits, that shield is tested. If the CME's magnetic orientation is just right, or just wrong, it can cause the magnetosphere to compress, ripple, or even tear open briefly. This creates geomagnetic storms, powerful space weather events with consequences far beyond the atmosphere. One of the most visible results of such storms is the aurora. The northern and southern lights, usually dancing near the poles, can suddenly expand, visible across much lower latitudes than normal. These vibrant displays of green and red light are created when charged solar particles slam into Earth's upper atmosphere, exciting atoms and causing them to glow. While beautiful, these lights often signal that something more disruptive is occurring above. When the sun skips a beat, modern technology feels the tremor first. Satellites orbiting Earth can be damaged or disabled. Communication systems, GPS signals, and even aircraft navigation can be affected. Astronauts aboard the International Space Station need immediate protection from increased radiation. In severe events, airlines may reroute flights away from polar regions to avoid potential interference with instruments. On the ground, the threat becomes even more serious. Geomagnetic storms can induce electric currents in long conductors like power lines and pipelines. These currents, not designed to carry such energy, can overload electrical grids, melt transformers, and cause large-scale blackouts. In March 1989, a CME caused a geomagnetic storm that knocked out power to millions of people in Quebec, Canada. The blackout lasted 9 hours and offered a glimpse into what a larger event might do to our modern infrastructure. Scientists often reference the Carrington event, the most intense geomagnetic storm ever recorded. It occurred in September 1859 and was powerful enough to spark fires in telegraph stations and cause auroras visible as far south as the Caribbean. If a similar event happened today, the damage could be catastrophic. Satellites would fail. Communications would collapse. Power grids could take months or years to fully recover. The rhythm of the sun includes these disruptions. They are not mistakes or accidents. Instead, they are part of a natural cycle of solar activity. Approximately every 11 years, the sun goes through a solar cycle, from solar minimum, when it is calmest, to solar maximum, when activity peaks. During maximum, the number of sunspots increases, and with them, the likelihood of flares and CMEs. This cycle, though predictable in length, varies in intensity. Some cycles are mild, others more turbulent. Helioseismology, the study of the sun's internal vibrations, helps scientists understand when and how these events might occur. By listening to the oscillations beneath the surface, researchers can detect changes in magnetic activity. This allows space agencies to forecast solar storms with some warning, though the exact timing and impact remain difficult to predict. Today, space weather monitoring is a global effort. Agencies like NASA, ESA, and NOAA operate satellites dedicated to tracking solar activity. The Solar and Heliospheric Observatory, SOHO, and the Parker Solar Probe are two major missions studying the sun in detail. SOHO watches for signs of incoming CMEs, while the Parker Probe flies closer to the sun than any spacecraft in history, measuring particles, fields, and the solar wind itself. These tools are crucial in preparing for when the sun's calm rhythm breaks. Despite our technological growth, humanity is still vulnerable to solar tantrums. Our dependence on electronics, satellites, and global communications makes the stakes higher. A single powerful flare could cripple satellites, throw off financial systems, or delay emergency services. Even power plants and oil pipelines on Earth can experience corrosion and inefficiencies from geomagnetic surges. Understanding this vulnerability has led to changes. Many satellite systems now include shielding and redundant controls to minimize solar damage. Electric companies have protocols to disconnect certain parts of the grid in anticipation of large storms. Pilots and astronauts receive radiation warnings when solar activity increases. These measures, however, are not perfect. A direct hit from a massive CME, especially one traveling fast and aligned with Earth's magnetic field, could still cause global disruption. Even biology is not untouched. Although Earth's atmosphere blocks most solar radiation, very high levels can influence the upper atmosphere, increasing radiation exposure at high altitudes. Some studies suggest solar storms might slightly affect human health, influencing heart rhythms or increasing anxiety in sensitive individuals. The evidence remains debated, but the possibility underscores the sun's reach, not just across space, but into our bodies. And yet, despite the danger, the sun's rhythm remains beautiful. Like a heartbeat, it pulses, usually steady, occasionally skipping, but always alive. These skipped beats remind us that even massive stars can be unpredictable. They are reminders of scale, of power, of the delicate balance we depend on without ever fully realizing it. Our ancestors knew something of this, even if they didn't know the science. They watched eclipses with reverence, tracked sunspot-like patterns in ancient records, and saw auroras as messages from the sky. Today, we have data, models, and space probes. But we still look up with wonder when the sky glows unexpectedly red. In the silence of space, where no sound travels, the sun speaks through energy. A sudden flare is its shout. A CME is its lunge. Each one a moment when rhythm turns into roar. But then, just as quickly, it calms again. The cycle resumes. The music continues. And Earth keeps spinning beneath it all. To live on this planet is to live within that rhythm, both its quiet lullabies and its unpredictable bursts. We build systems to shield ourselves. We study its patterns, but we cannot ignore its influence. Even now, every heartbeat of the sun echoes across our atmosphere, across our power lines, and across the technology we rely on daily. So when the sun skips a beat, we notice. Not with ears, but with systems. With sensors, with lights in the sky, with power surges on the ground. And in those moments, we remember that Earth is not isolated. It is part of a vast, dynamic system, pulsing, breathing, and responding to forces far beyond our control. The next time your lights flicker, or a GPS signal delays, or you glimpse unusual colors at night, it might just be the sun, skipping a beat once more. A brief moment of disorder in its otherwise ancient rhythm, and a reminder that even the heart of the solar system can falter, if only for a moment. The sun leaves no journal behind. It does not write in ink or carve its story into stone. And yet, across Earth, hidden in rings of trees, layers of ice, and bands of rock, the sun's memory endures. These are not memories in the traditional sense, not emotions, not thoughts. But they are records, traces, a coded rhythm preserved in nature itself. While the sun has no voice, it has left behind a symphony of evidence, scattered across the surface of its favorite planet. Scientists call this solar memory proxy data. Because we cannot travel back in time to watch ancient flares or count sunspots from centuries ago, we rely on Earth's natural archives. Each year, a tree adds a ring. Each snowfall adds a layer to polar ice. Each volcanic eruption coats the land in ash, trapping particles and radiation. In these layers, the sun's behavior is quietly recorded, a language written in growth, ice, and sediment. Start with the trees. In many temperate regions, trees grow a new ring each year. The thickness, density, and even composition of each ring reflects the climate and atmospheric conditions of that season. During years of strong solar activity, increased ultraviolet radiation subtly shifts weather patterns, temperature, and cloud cover, all of which affect how trees grow. Narrow rings may point to cooler, cloudier years. Wider ones may signal warmer, more active solar cycles. Scientists can analyze these patterns with microscopic precision, reading the sun's rhythm like notes on a page. Then there is the ice, ancient, silent, and stunningly precise. Deep in Greenland and Antarctica, ice cores have been drilled that reach hundreds of thousands of years into the past. These cores preserve bubbles of ancient air, along with particles like beryllium-10 and carbon-14, isotopes created when cosmic rays from space interact with Earth's atmosphere. The intensity of these rays is directly influenced by solar activity. During times when the sun is strong, its magnetic field blocks many of these rays, leading to fewer isotopes. In weaker solar cycles, more cosmic radiation reaches Earth, creating higher levels of these markers. By measuring these traces, researchers can reconstruct the sun's strength and cycles over vast stretches of time. Even the rocks remember. In layers of sediment, in frozen lava flows, in lake beds untouched for millennia, scientists find mineral and chemical shifts that correspond with solar events. These rocks don't change overnight, but over decades, centuries, and millennia, patterns emerge. The Earth absorbs the sun's energy and reflects it back slowly, layer by layer, in everything from isotope concentration to magnetic alignment. Paleomagnetism, The study of Earth's past magnetic fields also offers clues. Since solar cycles can influence the planet's magnetosphere, ancient rocks can retain the magnetic mood of the sun at the time they were formed. Together, these records allow us to map the sun's past in astonishing detail. We know, for instance, that solar activity was unusually low between 1645 and 1715, a period known as the Maunder minimum. During this time, very few sunspots were observed, and the Earth experienced unusually cold winters, part of what's sometimes called the Little Ice Age. Tree rings, ice cores, and historical records all confirm this solar lull. What's remarkable is that the sun's silence from that era wasn't forgotten. It was encoded into Earth itself. These records are not merely scientific curiosities. They have real consequences for understanding our climate, our technologies, and our future. Knowing how the sun behaved in the past allows scientists to build better models for the future. It helps us distinguish between natural climate fluctuations and human-driven changes. It shows us the range of rhythms our star is capable of, from gentle warmth to powerful, erratic flares. Solar memory has also helped us understand rare but significant events. The Carrington event of 1859, for example, is the strongest geomagnetic storm on record. Telegraphs sparked and failed. Auroras were seen as far south as the Caribbean. Though it predates modern space technology, ice cores contain a spike in radiation matching that event, proving its solar origin. More recently, in 2012, a CME of similar magnitude missed Earth by just 9 days. Had it hit, modern life would have felt the sun's full fury. These historical and near-miss records serve as both warning and wonder, evidence that the sun's mood swings are more than theoretical. Perhaps the most poetic aspect of this memory is how indirect it is. The sun does not mark years. It does not leave dates. It simply pulses. And in those pulses, everything on Earth adjusts. Trees grow differently. Ice forms slightly altered layers. Rocks shift in chemistry. It is as if the entire planet tunes itself to the solar frequency, not consciously, not deliberately, but inevitably. Earth is a listener, and in its body, the sun's music is written. There's beauty in the quiet persistence of this record-keeping. These natural archives were never meant to be read. They were not created for our benefit. Yet they exist, and when we learn to read them, we step into a timeline far longer and more detailed than any human civilization could have maintained on its own. Our books and servers may vanish, but a glacier's memory is slow and stubborn. And still, these records are not permanent. As Earth warms and glacier melt, we risk losing some of the longest and most reliable solar records available. Trees die. Ice cores become harder to drill. Sediment is disturbed by development. In many ways, we are erasing the very tools that help us understand the sun's story. Scientists around the world now race to gather this data before it vanishes, to decode the solar rhythm before the record is lost. In this sense, we are archivists of a cosmic symphony. We are listeners, analyzers, and, ultimately, storytellers. We take these hidden patterns and bring them to life, not just for knowledge, but for meaning. To know the sun is to know the history of Earth's surface, its atmosphere, its life cycles. It is to understand not just how we live now, but how we have always lived, in quiet response to a burning sky. The connection between solar activity and human history is still being uncovered. Some historians suggest that shifts in solar output may have played subtle roles in the rise and fall of civilizations, influencing climate, crop yields, and even migrations. While the links are complex and not always direct, they hint at something larger. Humanity has always lived in the shadow of the sun's mood. We build calendars, cultures, and myths around it. But it also leaves fingerprints in the dust beneath our feet. In Japan, ancient records of auroras exist in temple scrolls. In Europe, monks scribbled sunspot sightings beside weather complaints. In North America, native oral traditions tell of strange lights in the sky that match what we now call geomagnetic storms. These human memories, combined with the geological ones, form a layered, interwoven archive, a memory not just in fire, but in words and wonder. What makes this even more humbling is how effortlessly the sun imprints these messages. It does not aim. It does not try. Its energy simply radiates, and Earth, soft, reactive, alive, records the echo. The tree does not know it is an instrument. The ice does not know it is a scroll. The rock does not know it is a witness. But they are. So when we speak of solar memory, we're not talking about consciousness. We're talking about rhythm preserved in silence. Data written without design. It is the sun's forgotten autobiography, scattered across Earth's surface in forms we are only beginning to translate. And this memory continues. With every solar pulse, Earth responds again. New tree rings grow. Ice forms fresh layers. Rock settles. The beat continues. Somewhere, someday, a scientist will take a core sample or study a ring and find the signature of a flare that hasn't even happened yet. The memory of the sun is always growing, even now, in real time. We are part of that process. Each time we record solar activity, each time we decode the past, we become keepers of that memory. Not just scientists, but viewers, listeners, dreamers. And in the quiet of night, when the stars shine and the world slows, we are reminded, the sun's story is Earth's story, too. The sun has always seemed eternal, rising every morning, setting every night, holding its place as the center of our lives. Its rhythm has been steady for billions of years, pulses of energy, solar cycles, the warm heartbeat of the solar system. But nothing in the universe lasts forever. And the sun, for all its stability, is slowly changing. Its music, the hidden rhythm that shaped the earth, the oceans, the skies, will not stay the same. At its core, the sun is a nuclear furnace, fusing hydrogen into helium. That process releases an immense amount of energy, enough to bathe Earth in light and heat, even across 93 million miles. But this balance is delicate. As hydrogen runs low, the core adjusts. The pressure builds. The temperature rises. The fusion process starts to shift. And slowly, almost imperceptibly, the tempo begins to change. The sun grows hotter with age. 1 billion years from now, its brightness will increase by about 10%. That might sound small, but for Earth, it's catastrophic. A slight increase in solar energy is enough to disrupt climate systems, trigger feedback loops, and boil away the oceans. We've seen how past fluctuations affected the Earth, from ice ages to extinctions. But those were temporary shifts. What comes next is permanent. This transformation won't be sudden. The sun will not explode or vanish. It will swell. It will burn with a deeper fire. Over millions of years, it will begin expanding into a red giant. Its outer layers will puff outward, engulfing Mercury, likely Venus, and perhaps even Earth. The solar rhythm will slow and deepen, turning from a high, bright hum to a long, drawn-out pulse. A funeral drumbeat for everything that once lived in its light. The sun's surface will cool as it expands, giving it a reddish hue. But the core will grow hotter, as heavier elements like helium begin to fuse. The balance will tip. Solar winds will strengthen, stripping away outer layers into space. The music of the sun, once harmonies, will become unstable, chaotic, roaring, a final performance that will echo across the cosmos. For Earth, the consequences are absolute. The rising temperatures will sterilize the surface long before the sun reaches us. The atmosphere will vanish. Oceans will be gone. The ground will melt. Tectonic activity may cease. The magnetic field, already weakening, will offer no defense. Earth will become a dead rock long before it is consumed. But long before that fiery end, the sun's shifting rhythm will already be felt. The 11-year solar cycle, once predictable, may grow erratic. Sunspots may vanish or multiply without pattern. Solar flares could intensify. The heliosphere, the vast bubble that shields the solar system from interstellar radiation, will shrink. Even the balance of the planet's orbits could subtly shift as the sun's mass changes over time. Everything connected to the sun will feel the change. This isn't just about heat or radiation. It's about structure, gravity, magnetism, particle flow, all of it tied to the sun's state. The same rhythms that once guided Earth's climate, tides, and biology will turn against the system that depended on them. The sun will no longer be a nurturing parent. It will become a force of dismantling. Not angry, not malicious, just transformed. And yet, it will still shine. For a time, perhaps even more brightly than ever before. But the warmth will no longer support life. It will be the heat of endings, of systems unraveling, of orbits decaying, of time catching up. A solar crescendo that ends not in silence, but in collapse. Eventually, the red giant phase will peak. The sun's outer layers will drift away into space, forming a glowing shell of gas, a planetary nebula. At its center, what remains will be a white dwarf, a dense, hot core no larger than Earth, slowly cooling over trillions of years. No more fusion. No more flares. Just a fading ember in the void. That white dwarf will no longer produce music. Its rhythm will be still, locked in place. A remnant. A memory. the final stage of a star that once gave birth to planets, light, and life. Earth, if it still exists by then, will be either a scorched husk or swallowed entirely by the red giant. All that we were, mountains, oceans, civilizations, will be gone. The solar system will continue in a diminished form, with cold gas giants orbiting a cold, dim relic. The great concert will be over. But until that moment arrives, the signs are building. Astronomers already observe solar changes. Small shifts. New data. The solar constant is not truly constant. Instruments detect tiny variations in output, solar wind strength, and particle flow. Helioseismology, the study of the sun's internal oscillations, gives us a glimpse into its hidden tempo. It's like listening to a heartbeat growing slower, heavier, more labored. For humanity, the urgency is not immediate. These changes unfold over millions, even billions of years. But the science is not speculation. It's physics. It's math. It's inevitability. The sun will change. The earth will suffer. And the melody that guided life will become a requiem. Still, there is something beautiful in the predictability of it all. Stars like our sun have followed this script across the galaxy for eons. This isn't a tragedy. It's a cycle. Birth, evolution, death, even for stars. The same process that will destroy Earth once gave it life. The same rhythms that led to ruin once seeded the seas with energy. The sun has not failed. It has simply played its part. Perhaps one day, long after Earth is gone, another world will orbit another star, and intelligent life will wonder what came before. Perhaps they'll find traces of us, our probes, our signals, our stories. Perhaps they'll study our star's final chapters and recognize the same pattern in their own. They'll know what to expect, and when to listen. The rhythm of stars is universal. For now, we are lucky. We live during the golden middle, a stable sun, a thriving earth, and the tools to understand the future. We can observe the changes, prepare for the long arc of time, and reflect on what it means to live in the glow of something so powerful and temporary. The music of the sun is still playing. The tempo is still steady, but the notes are shifting. And one day, not today, not tomorrow, but someday far beyond our reach, the music will change. And when it does, the silence that follows will carry the memory of all that once listened. When a star dies, it does not disappear. It transforms. What was once a nuclear furnace becomes something smaller, denser, quieter. After the sun reaches the end of its red giant phase, after it has shed its outer layers into space and consumed what it can, it will settle into stillness. The remaining core will become a white dwarf, a hot, glowing ember the size of Earth but with the mass of the sun. There will be no more fusion, no more energy creation. But the story doesn't stop there. Because even in its silence, the sun will leave echoes. The white dwarf is not truly dead. It still glows, slowly radiating away its heat into the cold of space. Over billions and trillions of years, it will cool, eventually becoming a cold black dwarf, invisible in the darkness. But that process takes longer than the current age of the universe. So for a very long time, this leftover core will remain, silent, dense, and glowing faintly in the cosmic dark. Its rhythm may be gone, but its presence lingers. This tiny object, born from the collapse of a giant, still carries the signature of its past life. Its gravity is immense. Any surviving planets, asteroids, or debris will still orbit it, albeit slowly, from afar. Their paths will be different now. With most of the sun's mass gone, the gravitational pull weakens. Orbits drift outward. Everything becomes more fragile, more uncertain. But even in this altered state, the former star continues to exert its influence. Around this quiet star, the ghosts of the solar system remain. Gas giants might still circle far out, changed but intact. Their moons could drift loosely, slowly. Dust clouds spiral through the vacuum, remnants of lost worlds. Some fragments of Earth, now long shattered, vaporized, or ejected, might remain in pieces. Perhaps a chunk of crust fused to a satellite. Perhaps an old spacecraft tumbling endlessly. Pieces of what once was, circling a star that can no longer give them light. But echoes aren't limited to motion. There are chemical and electromagnetic traces left behind, memory coded in particles and photons. Some of the elements formed inside the sun, carbon, oxygen, neon, now drift freely in the cosmos. They will mix with the interstellar medium, seeding new clouds of dust. And from those clouds, one day, new stars will form. New planets. New chances. The echo of our sun becomes part of something else. Even the shape of the planetary nebula, the luminous shell expelled before the white dwarf emerged, holds memory. Its structure is shaped by magnetic fields, solar winds, and the motion of planets. Telescopes on distant worlds could one day look back at this faint nebula and learn something about the sun's life just from its shape. Even after death, it teaches. It informs. And somewhere, riding on radio waves or buried in the cold remains of probes, will be our messages, digital signals, metal discs, golden records. Human voices. Maps of our DNA. Greetings in dozens of languages. These, too, are echoes. Not of light or gravity, but of life. The sun may no longer shine, but the civilizations it once warmed might still be known, not because of what they built, but because of what they left drifting behind. Astronomers studying white dwarfs in other systems have already detected debris disks, planets with distorted orbits, and even signs of former atmospheres stripped away. Some white dwarfs bear the chemical fingerprints of rocky worlds that once orbited too close and were torn apart. These remnants, analyzed through spectroscopy, act like forensic evidence, clues that a planet once lived and died in that star's embrace. Earth may leave behind a similar record, invisible but readable, encoded in the light absorbed by what remains. Even in this final stage, the story continues. The sun's gravitational pull still shapes the fabric of space. Its mass bends light. It creates gentle gravitational waves as planets pass and orbit. It holds a presence, like a ghost whose footsteps still echo in the halls of the solar system. Time stretches unimaginably here. The white dwarf will outlast the memory of Earth, the life of our galaxy, and perhaps even the fabric of stars as we know them. It will cool slowly, losing heat molecule by molecule. Its pulse may be gone, but the signature lingers. Telescopes in some future civilization, orbiting an alien star, might one day catch the faint glow of this cooling corpse. They might calculate its age. They might detect planets that once held life. They might wonder what happened here, who lived, who dreamed, who watched this star from the surface of a little blue planet. This phase is also quiet. The storms, the flares, the blinding eruptions, all of it has stopped. There are no more sunspots. No coronal mass ejections. No nuclear chaos. The white dwarf is stable. It spins slowly. It cools constantly. Its light is faint but steady, like the last coals of a fire long extinguished. The violence has passed. What remains is peace. And in that peace, there is a kind of reverence. The sun is no longer a threat. It is no longer a creator. It is something in between, a reminder, a relic. It does not demand attention, but it holds it. The solar system is quieter now, perhaps even more beautiful. The chaos has faded. What's left is balance. Cold, dark, silent balance. The cosmic echoes of the sun are not bound to physical matter. They exist in energy and in space. Gravity wells, bent light, old orbits. They ripple outward across the stars, mixing with other stories, other remnants. The Milky Way is full of such whispers, the remains of stars, the paths of long-lost planets, the shadows of ancient light. Our sun will become part of that tapestry, no longer dominant, but still present. Even black dwarfs, the final, frozen form of white dwarfs, are theoretical at this point. The universe isn't old enough for one to exist. But one day, the sun will reach that state. It will no longer emit light. It will be invisible, a dead object in an empty part of space. But mass does not vanish, and gravity never forgets. Even when all heat is gone, the pull remains. The echo continues, silent and strong. There's something profound in knowing that the sun, for all its power, will eventually fade into quiet. Not with a bang, not with fire, but with stillness. It does not rage against the end. It becomes a record, a quiet sphere carrying the weight of its own history. We, too, are echoes. Everything we've built, written, loved, all of it existed under this star's light. Our seasons, our songs, our stories, born of the solar rhythm. When the sun is gone, our traces may still be there, floating, orbiting, waiting to be found. Or maybe not. Maybe no one will ever see what we leave behind. But the echo is real. It happened. And that matters. In this final phase, the sun offers us one last lesson. Nothing truly ends. Energy changes. Matter shifts. Stories continue. The rhythm may fade, but the memory remains, not in sound or sight, but in the invisible patterns left behind. The earth is gone now. its ashes scattered or swallowed. The planets are silent. But the sun, now quiet, carries all of it in its core. It is no longer a light in the sky. It is a monument to all that came before. A glowing echo in the dark, soft, steady, eternal. Format, paragraph style, emotionally calm, sleep-friendly, fitting for your Stellar Sleep Tales channel finale. Underscore 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 underscore. The stars are not silent. They may not speak in voices or tones we recognize, but they resonate deep within their cores. They pulse with waves of pressure and light. Each star carries a rhythm, a signature frequency, a kind of music that tells the story of its birth, life, and inevitable end. Our sun, the great furnace at the heart of our solar system, has always sung. And Earth, for 4.5 billion years, listened. From the beginning, Earth was tuned to the sun's rhythm. Oceans danced to its cycles. Winds blew in time with its energy. Life emerged in the gentle intervals between sunrise and sunset, shaped by warmth, guided by light. Even the smallest organisms pulsed with the echo of solar timing. Every breath, every bloom, every heartbeat, a quiet harmony with a giant far above. As the sun aged, its song changed. The tempo slowed, grew heavier. The final notes came with heat and silence. Earth faded. The air vanished. The land cracked. But even in those last quiet centuries, the planet still moved in time with the dying cadence of its star. And when the sun finally let go of its outer shell and retreated into a white dwarf, the symphony did not end. It transformed. The sun's music was never confined to sound. It was in the motion of planets, in the direction of comets, in the twisting of magnetic fields. It lived in radiation waves, in fusion pulses, in the gravitational pull of orbit. It vibrated through everything, not to be heard, but to be felt. Now, long after the Earth is gone, that rhythm still lingers. The white dwarf that remains is quiet, but it holds the memory of every beat it ever produced. The planetary nebula surrounding it glows briefly, a visual echo of the music that once was. As the light fades, particles drift into space, carrying with them fragments of the symphony. These fragments will join with others, the echoes of distant stars, the whispers of ancient galaxies, and compose new songs elsewhere in the universe. Every star sings. Every planet listens. And when planets die, their stories are not lost. They become part of the larger harmony, the cosmic rhythm that never stops playing. Earth's story was short compared to the lifespan of the universe, but it was rich, layered, and filled with intricate movements. It began as a pulse in a disk of dust. It grew into symphonies of rain, thunder, laughter, and silence. It ended in stillness, but it never truly ended. Somewhere, perhaps, a being on another world looks at a distant white dwarf and wonders what once circled that faint ember. They may measure its composition, calculate the lost mass, read the chemistry of the debris. They may listen to its vibration and find patterns that don't match anything else. And in those patterns, they may feel something. Not a sound, but a message. A rhythm. The solar system is quieter now, but not empty. Each remnant, a drifting rock, a warped orbit, a speck of metal once part of a satellite, carries with it the rhythm of home. It is not loud. It does not demand attention. But it moves in time. And for those who know how to listen, it is still playing. The sun's secret symphony was never just about physics. It was about life. About the bond between star and world. About how energy becomes time, and time becomes memory. Our ancestors saw the sun as a god. Scientists saw it as a machine. In truth, it was something in between, a performer in the grand concert of the cosmos. And Earth, for a while, was its most devoted audience. We may never hear that music with our ears, but we feel it, in cycles, in instincts, in sleep and waking. The body knows what the mind forgets, that we were born under rhythm, raised by light, shaped by a cadence older than words. And long after we are gone, that pulse continues somewhere. The symphony never ends. Even in silence, there is structure. Even in darkness, echoes remain. The particles once touched by sunlight will go on to touch others. The heat that once stirred the oceans will one day stir new clouds. The photons that bathed Earth's forests still travel outward endlessly. What we were, our thoughts, our dreams, our breath, was all part of a single song. And you, the listener, are part of it too. You've followed this story not with logic alone, but with feeling. You've heard not sound, but rhythm. Not fact, but meaning. You've drifted through time, across heat and silence, through birth and collapse, and now you are still. Listening. That stillness is not emptiness. It is the space between notes, the pause before the next movement. Somewhere, another star is beginning to sing. Another world is learning its pattern. The music continues. So close your eyes now. Let the rhythm settle into your breath. Let your thoughts quiet. Let your body rest. The universe is not silent. It is singing softly, not in tones or lyrics, but in motion, memory, and light. You've heard the sun's secret symphony. Not through ears, but through feeling. Sleep now, and let the rhythm continue inside you.